Hello everyone, my name is Dominik. My talk is about a problem called string range matching. This is joint work with Juha Kärkkäinen and Simon. So the problem discussed in this talk is a generalization of the classical exact string matching problem, in which we're given text X and a pattern Y, and the goal is to compute the starting positions of all occurrences of the pattern in the text. For example, in the text below, we have two occurrences of the pattern BA at position 9 and 1. And in pattern matching, usually assume that we cannot pre-process the text. In particular, we cannot index it. And we can equivalently define string matching as follows. If by xi we denote the suffix of x starting at position I, then the exact string matching problem asks to enumerate all the suffixes of the text such that y is a prefix of xi. And this relation between the pattern and suffixes of the text is what we generalize to obtain the new problem we call string range matching. In string range matching, we are given a text x as before, but rather than one pattern y, this time we have two patterns, y and z. And the goal is to compute all positions I in the text such that the suffix xi belongs to the lexicographical range defined by pattern y and z, or formally that this inequality is satisfied. And by m now we denote the combined length of two patterns. And this indeed is a generalization of string matching because we can solve string matching as a special case. So we just have to set the other pattern, z, to be y concatenated with hash, a special symbol that is larger than all other normal symbols. And as you can see from this example, if z is defined like that, then all the suffixes of the text that belong to the range, lexicographical range defined by these two patterns, have y as a prefix. So the output of string range matching on this instant will be the same as string matching. And we can also define a simpler problem called one-sided string range matching, where we're given a text and a pattern, and the goal is to compute all suffixes of the text smaller than the pattern. And this is useful to consider because, first of all, any two-sided range of strings is a combination of one-sided ranges. And second, this variant is more similar to exact string matching in that there is only one pattern. So it's simpler to think about, and the algorithm also are simpler. However, we don't know whether this variant of the problem is theoretically easier than two-sided variant. All algorithms in our paper have the same complexity. So one of the applications of this problem is in suffix array and Barrows-Wheeler construction. We are aware of at least 3 implementations where this problem, where string range matching appears as a subproblem. Okay, so we'll now review the time-space complexity of the problems mentioned so far. So exact string matching is a classical problem in stringology with dozens of algorithms. Many of them have linear time complexity, such as the famous Knuth, Morris, and Pratt. Some of them, in addition, also use constant extra space, which is the space in addition to input and output. And these are called time-space optimal. So this is a summary of selected linear time exact string matching algorithms that we will use as a basis to solve a string range matching problem. So we have Knuth, Morris, and Pratt, using order M space. We have a weak version of algorithm by Galil and Seyferaz using log M space, and we have a time space optimal of Kroshmore. And they all share few features, but the key feature is that they all perform left to right matching of the pattern. Any algorithm that starts matching of the pattern from in the middle or from the end is not suitable for string range matching, and you will see why in a minute. They also share some other common features, such as that they scan the text left to right. So those are streaming algorithms. They are comparison-based and also alphabet independent. So this is a summary of algorithms for string range matching. So the first algorithm is due to Karkainen from 2007. It's based on KMP, and so it's using order of M space. But in this talk, we will discuss the remaining two algorithms, which are the main contribution of our paper. The first one is based on the algorithm of Khalil and Seyferaz. It runs in linear time. It's using order log m extra space, but it only works for the counting variant of the problem. So we can only count how many suffixes of the text are smaller than the pattern, but we cannot enumerate them. The second algorithm is based on Kroshmo's algorithm and runs in n log m time, and it's using constant extra space. In addition, in the paper, we also described two algorithms that are time-space optimal if we slightly cheat about the extra space aspect. We call them cheating algorithms. So the first one, they're both based on Kroshmo's algorithm. The first one requires permission to overwrite the patterns. And the second one requires permission to read the output, and it only works for the reporting version. So we will see details of these algorithms in a minute. So just so we're on the same page, these are the two problems that are relevant for the rest of the talks. So we have string matching problem, in which we want to enumerate suffixes of the text that have pattern as a prefix. And we have one-sided string range matching, where we are interested in suffixes of the text that are smaller than the pattern. And all our string range matching algorithms use the same basic approach. Suppose we aligned the pattern with position I in the text. We compute the longest common prefix of the pattern and suffix starting at position I, we call it L. And now we can determine whether the suffix of text starting at position I is smaller than the pattern or not, just by doing one extra symbol comparison. So in this case, this suffix is not smaller because we have a mismatch here like this. So then what we do is what most string matching algorithms would do. We compute the shortest period of the matching pattern prefix, we call it P, and we shift the pattern by P positions in the text. So we increase I by P and decrease L by P. So now the pattern will be aligned with the text like this. And then we repeat this. So again, we keep matching the symbols until we get a mismatch. Then now we can decide about the status. Now we can determine the status of suffix I, whether it's smaller or larger than the pattern, and then again compute the shortest period. And now you may have two questions. First of all, how we compute the shortest period of the matching pattern prefix. And the answer is that this is provided by the underlying string matching algorithms. Because this is like a basic framework that all the algorithms, all the string matching algorithms that we use as a basis, they work like that. So they somehow compute P, and we won't get into that. And in some cases, they actually don't compute exactly P, but something smaller that is good enough to achieve linear time. But we won't explain that. What's more relevant for the problem is what is the status of the suffixes at the skipped positions. So are the suffixes between positions I and I plus P smaller than the pattern or not? So let's have a closer look at this. So let's take one of those positions between I and I plus P. In this example, let's see at I plus 2. So this is the position J. It's right there. And now let L prime be the longest common prefix of the pattern and the suffix of text starting at position J. So we have pattern aligned with two positions in the text, I and J. And now we have the following lemma. So let's break it down. J plus L is the position of a mismatch if we align the pattern with position J in the text. So it's this position in the text. I plus L is the position of a mismatch if we align the pattern with position I in the text. And the lemma says that the first mismatch is in the text is before the second one. And This is easy to see because if the mismatch at position j plus l would extend at least until I plus l, then there would be a border here because we have a pattern matching with itself at some position. So this would be a border, and we would have a period of length 2 in this case. And in general, we would have a period shorter than p. And p is already assumed to be the shortest. So this cannot happen. And this simple fact is used by many string matching algorithms to conclude that there is no pattern occurrence at any of those positions. However, this observation is useful also for our problem in that if we want to compute L prime, we don't need the text because all the necessary symbols are in the pattern, because we have this long matching pattern prefix of the pattern, and now we are comparing the pattern against some suffix of the pattern that we know there will be a mismatch before this mismatch right there. So we can formally write this as follows. The suffix of text xj is smaller than the pattern if and only if the suffix j minus I of the pattern is smaller than the pattern itself. Okay, so string range matching is a lot like pattern matching. The main difference is how the algorithms deal with the skipped positions j. In exact string matching, we know that there are no occurrences of the pattern there, so we just ignore those positions completely. We don't do anything. In string range matching, however, we have to determine what is the status of those suffixes, whether they are smaller than the pattern or not. And so as we saw on the previous slide, fortunately, this entirely depends on the pattern. So the idea is to pre-process the pattern to answer this. And this is easy to do if we have lots of space. For example, if we have order m space, we can adapt KMP algorithm to do that. In fact, we can show that even less space is enough. We just need m bits. But we want to be time space optimal, ideally. So we want to use only constant extra space. So m bits is like way too much. So let's see the idea of the first algorithm. We only allow order log m different shift lengths of the pattern. And for each shift length, we pre-compute the number of skipped suffixes that are smaller up to that shift. And now, whenever normally in the algorithm we would do a certain shift by a certain amount of positions, that we call it optimal shift, instead we do a shorter shift, and this shorter shift is the largest pre-computed shift that doesn't exceed the optimal shift, right? And if we pre-compute those shifts correctly, this algorithm still runs in linear time. And by correctly, I mean that they have to cover the range from 1 to m evenly in the multiplicative sense. So the ratio between consecutive shifts have to be constant. However, with each shift here, we associated only the number of suffixes, not their positions. And it's not clear whether we can recover or recompute this information. So this algorithm only works for the counting version of string range matching. And it runs in linear time and uses order log m space. So here's the idea of the second algorithm that will run in n log m time and use constant extra space. So to do that, we reduce the problem to a simpler problem. We call it restricted one-sided string range matching. And in that problem, we're given a text and a pattern, and we want to compute all this. We want to enumerate all the suffixes of the text that are smaller than the pattern, but that also have the LCP with the pattern of length at least 2/3 of m. And we can solve this restricted problem in linear time and constant extra space using a modified Kroshmos algorithm. So to solve a general case, we just have to run this algorithm log m times, every time reducing the pattern length by 1/3. And then the output is a disjoint union of the results produced by individual calls. So finally, let's have a look at the cheating algorithms. So as we mentioned before, m bits is enough, or in fact, in some cases, even less than m bits is enough to store the information about the skipped suffixes. And the idea behind cheating is that we don't have those bits, so we create them somewhere. One algorithm The first algorithm finds the longest prefix of the pattern that occurs elsewhere in the pattern and use that prefix as the storage area. And these overwritten symbols of the pattern can be restored at the end of the algorithm from the other occurrence of the repetition. The second algorithm creates the bits in the output in some sense. So during the algorithm, we keep track of the longest matching prefix seen so far. And whenever we have to do a shift, we copy the information about the skipped suffixes from the output. So we copy those bits, telling us which suffixes are smaller. So in some sense, this is our memory right now. That we fill the output with information in time. And this only works for the reporting version, because in the counting version of the problem, where we just count the number of suffixes, there's not enough useful input we could use. So this is a quick summary of these new algorithms. We give two algorithms that are, if we consider the product of time and extra space, both of these algorithms are off from time space optimal by a factor of log m. And one of them only works for the counting variant. And also, we give two algorithms that are time space optimal, but under some special assumptions. So finally, let me tell you a bit about open problems. So there are many questions you could ask. For example, what can we do in linear time without cheating? So for example, can we do reporting in sublinear space? Can we do counting in sublogarithmic space? Or you could also ask orthogonal question, what can be done in constant extra space without cheating? Can we do faster than n log m? Or if we can't, can we at least reduce the number of passes over the text? Perhaps make the algorithm possible so that it's a streaming algorithm. It only does one pass over the text. Also, trade-offs would be interesting. And related to that, there are some interesting lower bounds we could try to prove. For example, is string range matching harder than the exact string matching problem? And our conjecture is that it is yes. So our conjecture is that we cannot solve string range matching in linear time and constant extra space without cheating. Other interesting questions, such as, is reporting harder than counting, or is the one-sided problem easier than two-sided? We don't know answers to these questions yet. And finally, if we cannot improve the algorithms, perhaps it would be interesting to provide lower bounds, so to prove that these algorithms are optimal. And that is all I have. Thank you.
Okay, thanks, Dominik. Any questions for the speaker? Yeah, Eric.
If the alphabet is very large and you have short patterns, you could have some. You could use some sort of heuristic, saying if some character appears but appear rarely in the text, you could answer some part of the question for some windows. Have you looked at special type of situation of?
No, we haven't specifically looked at the alphabet size too much, because the underlying algorithms, they work for unbounded alphabets. They use only comparisons. So I think they sort of implicitly handle these cases. I'm not sure if these heuristics would help.
Any more questions, Maxine?
So your result suggests that you have a kind of n log n or n log m lower bound on time.
N log m.
Is it what you suggest?
This is not. Well, I wouldn't go as far as to say that. I actually think this could be improved somehow, perhaps using bit parallelism, for example. But at least the conjecture is that we cannot go to linear time in constant extra space. So I believe there is some slack.
Okay, well, if there are no more questions, let's thank the speaker again.